Hello again. In this video, we're going to continue our discussion of molecular orbitals and molecular orbital theory, and we're going to expand what we did in the previous video to include homo and heteronuclear diatomic molecules that are bigger than those that just use 1s orbitals. So, we looked at bonding in hydrogen and helium containing species, and now we're going to ask the question, what happens after hydrogen and helium? Well, after helium, of course, comes lithium. And we are going to consider the bonding in the hypothetical molecule dilithium. Now, we are not going to worry about the 1s orbitals, the sigma 1s bonding molecular orbital and the sigma star 1s antibonding molecular orbital, because they are completely filled and therefore kind of cancel each other out. So we're simply going to be looking at the valence electrons in these species. Now, we know that the hypothetical molecule dilithium would have two valence electrons. So we can place both of those valence electrons in the lower energy sigma 2s bonding molecular orbital. Now this molecular orbital is going to be very similar to the one formed by the positive overlap of the 1s orbitals in dihydrogen. It just uses 2s orbitals instead because those are the valence orbitals. Okay? Well, to calculate the bond order, we would take the 2 electrons in the sigma 2s bonding molecular orbital, subtract the 0 electrons from the sigma star 2s antibonding molecular orbital, and divide by 2, and that would give us a hypothetical bond order of 1. So what that means is that, in theory, the dilithium molecule should exist, and it would have a single bond. For the hypothetical diberyllium molecule, now because each beryllium atom has 2 valence electrons, that would be a total of 4 electrons. Once again, we would place 2 electrons in the sigma 2s bonding molecular orbital, but then we would also populate the sigma star 2s antibonding molecular orbital with 2 electrons, leading to a predicted bond order of 0. And the first molecule, of course, would be predicted to be diamagnetic because it has no unpaired electrons. Now, things start to get a little complicated after beryllium because after beryllium comes boron. And now we have not just s atomic orbitals, but we have p atomic orbitals. Now, if we imagine a bond between two atoms that have p orbitals on them with electrons in them, there are 2 ways in which the p orbitals can overlap to form molecular orbitals. In one of the ways, the p orbitals that are on the internuclear axis, that is, those that are pointing directly towards each other, can form sigma molecular orbitals, and that can be formed by head-to-head overlap of p orbitals. So, this diagram shows 2 p orbitals on adjacent atoms, and we'll just arbitrarily define the axis that connects the 2 nuclei as the z-axis. So these would be the p sub z orbitals on the 2 bonded atoms. And in the way that's depicted here, the 2 p orbitals combine in a positive way. That is, we add the p sub z wave functions together. That results in increased electron density between the 2 nuclei, as shown by the orange blob between the nuclei. That would be called a sigma 2p bonding molecular orbital, assuming that these were 2p orbitals. On the other hand, we could combine them in a negative fashion, that is, by subtracting them. That would result in the situation shown in the bottom right, in which now there is a nodal plane between the 2 nuclei. That results in decreased electron density between the 2 nuclei. That would be an antibonding molecular orbital, and we're going to call that the sigma star 2p antibonding molecular orbital. Okay? Now, that's only one of the 3 p orbitals on each of the atoms. They also have 2 additional p orbitals that are not pointing between the atoms, but in fact they are perpendicular to the axis between the 2 nuclei. Those can only overlap in a sideways fashion, and when we overlap p orbitals in a side-to-side fashion, as we learned before, we form not sigma molecular orbitals, but pi molecular orbitals, which are not cylindrically symmetrical. So, let's take, for example, the p sub x atomic orbitals on the 2 adjacent atoms, and we'll arbitrarily define the axis pointing up and down as the x-axis. If we combine these 2 p orbitals on adjacent atoms in a positive way, that is, if we add the wave functions together, we end up with what's called the pi 2p molecular orbital. And again, as you can see, there is electron density above and below the z-axis. That is characteristic of pi orbitals, as we talked about in our discussion on hybridization. But we can also combine them in a negative fashion, that is by subtracting the wave functions, and that results in a nodal plane. In this case, it's in the xy plane, which is perpendicular to the bond axis, again resulting in a decrease in electron density between the two nuclei, which disfavors bonding. That then will be an antibonding molecular orbital, and we will call that the pi star 2p molecular orbital. Now, because there are two such p orbitals like this, that means we can get two pi 2p bonding molecular orbitals and two pi star 2p antibonding molecular orbitals. And when we simply look at the molecular orbitals that come from the p orbitals, we see an energy level diagram that looks like this. On the outside, we have the p orbitals on the starting atoms. And then we can see, once again, we're combining a total of 6 atomic orbitals, so we expect to get out a total of 6 molecular orbitals. And those will include the sigma bonding molecular orbital, 2 pi bonding molecular orbitals that are at the same energy. And notice that those are lower in energy than the starting atomic orbitals. But we also end up with 2 pi star antibonding molecular orbitals, and up here way at the top, a sigma star antibonding molecular orbit as well. So again, a total of 6 p orbitals on our starting atoms result in 6 molecular orbitals, 3 of which are bonding and 3 of which are antibonding. Now, let's put it all together and see what it looks like. And here is a molecular orbital energy level diagram for diatomic species that have valence electrons in the 2s and the 2p sublevels using all of the 2s and 2p orbitals. I'm going to label them from the bottom to the top, and this is something that you should be able to do. So the overlap of the 2s orbitals on each atom result in a sigma bonding and a sigma antibonding molecular orbital. So the lowest energy is going to be the sigma 2s bonding molecular orbital, followed by the sigma star 2s antibonding molecular orbital. Above that, we have the sigma 2p bonding molecular orbital, and we have 2 equivalent pi 2p bonding molecular orbitals. Above that, now we have antibonding molecular orbitals that come from the 2p orbitals. We have the 2 equivalent pi star antibonding 2p molecular orbitals. And at the very top, we have our sigma star 2p antibonding molecular orbital. Now, I will point out that this is a bit of an oversimplification because in certain cases, some of these molecular orbital energies begin to switch. But for this class, for this year, we are going to assume that this is the molecular orbital energy level diagram we will use for diatomic species. So, let us now go through and look at molecular orbital descriptions of the diatomic molecules dinitrogen, dioxygen, and difluorine. And let's begin with N2. We will begin by counting valence electrons. Again, we're not worried about the 1s electrons. So the dinitrogen molecule has 10 valence electrons. And we're going to start by putting those simply in the lowest energy sublevels to begin with. Sigma 2s, sigma 2s star, sigma 2p, pi 2p, pi star 2p, and sigma star 2p. So starting at the bottom, 2 electrons in the sigma 2s, 2 electrons in the sigma star 2s, 2 electrons in the pi 2p, and 1, 2, 3, 4 electrons in the pi 2p. Now, we can write the molecular orbital electron configuration for this simply by listing those. That will be sigma 2s 2, sigma star 2s 2, sigma 2p 2, and pi 2p 4. If you calculate the bond order, you will see that that gives you a bond order of 3. Okay? We've got a total of 2, 4, 6, 8 electrons in bonding molecular orbitals. We subtract 2 electrons in antibonding molecular orbitals to give us 6. Divide that by 2, and that gives us 3. Well, what do you know? If you go back to the localized electron model and draw a Lewis structure for dinitrogen, what do you have? You have a nitrogen-nitrogen triple bond. Okay, how cool is that? Here's an example of where the bond order that is predicted based on molecular orbital theory matches exactly the bond order that you would calculate using the localized model. Now, let's consider O2, and I'm going to label these for you, and then I'm going to ask you to pause the video and maybe try filling it in yourself and see what you get. I guess I should have done this in advance, shouldn't I? Oh well. All right, if you're back, you see that the dioxygen molecule has 12 valence electrons, and I will begin by putting those in the lowest energy sublevels. So 1s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now we see, because we've got 2 more valence electrons than an N2, we have to populate the pi star 2p antibonding molecular orbitals, which is going to weaken the bonding. If you go through and write the electron configuration, you'll simply add 2 more electrons in the pi star 2p. I'm not going to do it for simplicity because you can do it yourself. But what you see here now is that because now we have 2 electrons in antibonding molecular orbitals, that actually gives us a bond order of 2. A general principle is that populating antibonding molecular orbitals, that is placing electrons into antibonding molecular orbitals, weakens bonding and therefore lowers the bond order. Now, once again, you see how cool this is, because if you draw a Lewis structure for the O2 molecule using the localized electron model, you see an oxygen-oxygen double bond. Once again, consistent with molecular orbital theory. However, what the localized electron model does not explain is the fact, the experimentally verifiable fact, that the dioxygen molecule is paramagnetic. Check this out. If you cool O2 down low enough so that it liquefies, you can actually suspend liquid oxygen between the poles of a very, very strong magnet. Okay? Now, that is because the O2 molecule has unpaired electrons, and there is no way to explain that using the localized electron model. But if you use the molecular orbital model, you can see very clearly right here, look at that, we've got 2 unpaired electrons, and that is a more accurate description of the bonding in O2. Now, just to finish things up, let's do fluorine, sigma 2s, sigma star 2s, sigma 2p, pi 2p, pi star 2p, and sigma star 2p. In the difluorine molecule, we've now got 14 valence electrons, and we're going to start placing those from low to high. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I didn't mention this before, but you noticed in O2 that the molecular orbital model follows Hund's rule as well. 4, 6, 8, 10, 11, 12, 13, 14. Okay? So you can write the energy level the electron configuration the way we did before, and now you can see that by subtracting the number of antibonding electrons from the number of bonding electrons and dividing by 2, you get a bond order equal 1. And once again, that is consistent with the localized model. And in the localized model, the F2 molecule has a single bond. So once again, it is consistent. Now, we can also do this with heteronuclear diatomic species, meaning diatomic things made up of 2 atoms, in which the 2 atoms are not of the same element. And they can be neutral molecules, they could be cations, they could be anions. Whatever it is, you treat it exactly the same way. You simply count the total valence electrons, use the same energy level diagram we've been using throughout, and fill it up, write the electron configuration, calculate the bond order, predict whether it's magnetic or paramagnetic, diamagnetic, and it all works out the same. Okay, so let's summarize all of this. The molecular orbital model, again, a molecular orbital is an orbital that spans the entire molecule, not just an atom within it. It is made by linear combinations of atomic orbitals. The strengths are that it correctly explains and predicts magnetism. It very often correlates correctly with the number of bonds that you would draw in a Lewis structure using the localized electron model. It also correctly explains and predicts relative bond energies and lengths, because as the bond order increases, the bond length decreases and the bond energy increases. And the reason that I'm teaching you this year is because if you go to college and study many, many sciences, after a year of general chemistry, you will take a year of organic chemistry, and you simply cannot understand organic chemistry unless you have the basics of molecular orbital theory down. So I hope that helped. Have a great day, everybody.